Hi everyone. Here's another example from functions used as models. So we're trying to set up a formula for a function that models a real-world situation. Here we have a right circular cylinder with height h and radius r inscribed inside of a cone with height 9 centimeters and radius 3 centimeters. Okay, so let me draw a picture and make sure everybody can figure out what I'm trying to describe here. So we have a cone with a radius 3 centimeters and a height of 9 centimeters. We are placing a cylinder inside of this cone so that it just fits. So we're making it as big as possible while still fitting inside, which means the base of the cylinder will sit on the bottom of the cone and the top edge of the cylinder will just touch on the outside of the cone. So this entire circular rim of the cylinder touches the outside of the cone. This still leaves us some flexibility for what exactly the cylinder looks like. We can still make the cylinder really tall and skinny, so it just fits inside of here, or really short and flat and wide. So we are trying to write a formula for the volume of the cylinder as a function of its radius. So the volume of a cylinder is a function of this r right here. Okay, so we can actually get a pretty good start. The real problem here is having to eliminate a variable. The volume of a cylinder, and any of these weird volume formulas, I would expect you to be able to remember the volume of a box. But for anything else, if I don't provide it for you, you can feel free to ask me for things like that during a test if you come in while I'm proctoring. Or if you're working on your homework, you can absolutely look these things up. I would say on a test, especially for you guys, since you might not be coming in with me proctoring, I'll try and be careful to provide any weird volume formulas as needed. This one's actually kind of an easy one. When you take a two-dimensional shape, so in this case we're taking a circle, a nice easy two-dimensional shape, and you just stretch it out to get volume, all you have to do is take the area of the base and multiply it by the height of the shape. So this would work just as well if we made a triangular prism. Excuse me, on again. The base of this thing is a triangle, and then we stretch it out and make it this tall triangular prism. We'd find the area of the triangle and multiply by the height. So whatever 2D shape you take, if you want to make a volume by stretching it out, just multiply the area of the 2D shape by the height of the volume, the height of the solid. Okay, so here, like I said, it's actually pretty easy to get the formula because it's this pre-existing formula that either you'll have or we could find. The problem is we're supposed to make volume a function of the radius, which means we should not have the height involved. We can't just ignore the height. It's not a constant. It's definitely variable. Depending on r, we'll have a specific h. It should definitely be possible for us to eliminate h, and the reason I assume that is that when I look at this picture, I can tell that once I choose an r, say I choose r equals a quarter or r equals 2, I don't just get to pick any old h. The height is determined by the cone, so we have to figure out how to get that involved in this problem. And actually, sort of like the sphere, I think it can be kind of helpful to just slice right through the middle of this and look at it as a 2D shape. So if we do that, slice right down the middle, the cone is just going to look like a triangle. And the the cylinder is going to look like a rectangle. So this is R and this is H. And maybe you don't have to draw it two-dimensionally to see this, but what I'm hoping we'll spot, this is a tricky one, so learn to watch for this. I work on it in Pre-Calc 2 as well because people tend to not be great at it. I have a couple of triangles I could use. In fact, I can see 3 right off the bat. One of them is right here. This is another one. And then one I'm definitely going to want to get involved, see if I can figure out where I put my red pen. I don't see it. Let's try highlighter. Is this big one, somewhat visible. So this is not a Pythagorean theorem problem. There's a couple of things that hint at this not being a Pythagorean theorem problem. One of them is the fact that I have 3 different triangles that all share the same angles. They basically all have a side with the same slope. The other is I can figure out a fair amount of information about horizontal and vertical sides, but I have no information in here about the hypotenuse. I could calculate the hypotenuse of the big triangle, but I still wouldn't have a hypotenuse for the little triangle, so I'd be getting another variable involved, which I don't love. So I'm just going to make a pick. Let's see. I'm going to use the top triangle, this little one right here, and then the big pink triangle. So similar triangles, if you don't remember, the idea is if you have 2 triangles that are basically just shrunk or stretched out versions of each other in such a way that all of the angles stay the same, then you can take the ratios of any 2 sides in the 2 triangles and they will be equal to each other. So for the little triangle, I know that the bottom is R. I have to somehow get H involved in this triangle because my whole goal is to eliminate an H. So if this is H, I would say we need to use the total height of 9 centimeters and say that the little triangle has to be 9 minus H. So again, this length right here is H, the height of the rectangle or the cylinder. If we want to figure out how much height is left at the very top of the big triangle, we'll take the total height of the triangle, 9, and we'll subtract the height of the rectangle, H. Okay, so that's our little triangle. We're trying to get rid of an H, so I'm going to choose this as my ratio, but it could be upside down and that would be completely fine. Setting it up this way is just going to make it a little easier to solve for H. In the big triangle, I actually know everything about the big triangle that I need. I have vertical side length 9 and horizontal side length 3. So we want to make sure we set these up in the same order we did for the small triangle. We did vertical side length over horizontal side length, so we'll do that again. Okay, and then our goal is to eliminate an H from our original formula. So I am going to do a couple of things. One is I'm going to say that 9 over 3 is 3. The other is I'm going to multiply both sides of the equation by an R. I still need to solve for H, so I'm going to go ahead and subtract 9 and then multiply both sides by -1. Okay, so H is equal to -3R plus 9. Back up in this original volume equation, I don't know why I'm writing V again. Here, we'll go like this. Pi r squared. We can now replace the H with this -3R plus 9. Feel free to switch order if you want to. 9 minus 3R would be great as well. And this is our volume formula. Again, I didn't ask you about reasonable domain, but I can say really quickly, our variable is R. The smallest possible R is 0. That gives us no more cylinder, but just a tall vertical line inside of the cone. The biggest possible value of R would be 3 centimeters. Again, that completely flattens out our cylinder and all we have is a circle, but we are looking for extremes. So our domain would be 0, less than or equal to R, less than or equal to 3. All right, that's it for this one. Thanks for watching.